I am here with my friend and honored guest, Dr. Josh Hiller from Adelphi University in Long Island, New York. And we are going to talk about our favorite graphs and why we like graph theory. So, Dr. Hiller, at this point, my students know the what of graphs and some of the how, but they don't know the why. And I want us to introduce them to some of our friends.
The why graph. The world is very complicated. And I think the most beautiful thing a mathematician can do is to describe a complicated phenomenon in simple terms. And perhaps even better than that is in simple to visualize terms. And what a graph allows us to do is in a very concrete way to abstract out enough complexity to where we can do this and we can model a lot of really beautiful things by using this very simple structure. So with graphs, you have a set of vertices, right? And these set of vertices can represent anything you want in the world. And then the only thing is that between those two vertices, you need to have some kind of relationship that exists or doesn't exist. For example, they could be related, right? So we could have our vertex set could consist of people, and we could have the relationship related. Okay, so Andrew, you and I, but that's a relationship that's symmetric. So if I'm related to you, you're related to me, right?
Mhm.
And so we can describe that really easily with a graph, just by having what we call an edge set, where in this case, the edges represent are related, or two people are related.
So the vertices are people on Earth. There's an edge between two people if and only if they consider each other relatives.
Right.
That way it's symmetric. Both people have to agree. It's not like I'm your brother. No, you're not.
Right. I'm your brother. That's not what mom says. Exactly. So in this case, we've been able to take something as complex as kinship, which is an entire subject of anthropology, and we've been able to boil it down to something that is, in a sense, essential about it and visualize it. And then we can ask questions like, are there any disjoint subgraphs? Or is it true that we are all related to some degree?
Yeah, we could have something like, what is average family size?
Yeah, we could ask what is average family size. Now, what's interesting is because you said if two people consider each other relatives, because if we ask the question, are these two people related somewhere along their family tree, then what we get is a complete graph.
Yes. If you say these people have some common ancestor.
Right. Then we get a complete graph, right? And then everyone is related to everyone through blood.
So we actually have like the DNA family graph and then the social family graph.
Right, the kinship graph.
Kinship graph and the DNA family graph would be the same vertex set, but the edges would be people have an edge if they have a common ancestor. And then everyone shares some common ancestor. That's not a controversial statement.
Then we get a complete graph. We know that we're all family at some point by blood. And actually, we don't have to go very far up the family tree. You can do a pigeonhole principle argument. And I remember Miklos Bona, who's a famous combinatorialist that I studied under for 2 days.
Under for 2 days?
Yeah, and then I dropped his class. He said that you only have to go back about 70 generations. And at that point, you run out of holes, or you run out of people, rather. And so you go back about 70 generations, two people somewhere in the family trees of any two people share an ancestor.
So what are your favorite graphs?
Yeah, so I was thinking about this, and I have a lot of graphs that I like a lot, but I think my favorite graph is a triangle.
Just 3 vertices and 3 edges like this?
3 vertices and 3 edges. Yeah. And the reason for this is because it's possibly, I think, as somebody that really likes data, one of the most interesting graphs for data analysis. And as someone that also likes history, it's a very interesting graph historically. So it's the simplest complete graph. But now let's say, for example, we want to embed this guy in a cube.
So this is a K3.
This is a K3.
The green one is a K3 because it has 3 vertices and all possible connections between the vertices.
Right, right.
No, I'd like to stop you for a second. I think actually we're a little bit underspecified here.
Uh-huh.
So we said that we need a vertex set and an edge set, and then we just blew that concept up.
Away. Okay.
So let's give what would the vertex set be here?
But it could be 1, 2, 3.
Okay, so my vertex set is 1, 2, 3. And then I'm gonna give my edge set. So how do you like to represent edges?
I like to represent them as ordered pairs,
Okay.
even though they do not need to be ordered. In fact, in the case of a K3, they are not ordered, but it's just easier symbol-wise for me to remember.
If you want to do that, that's fine. I have no objections. And we have friends who don't even use symbols between the.
Yeah, correct. Okay, so you have this really pretty graph here. And so now let's look at some interesting properties. So let's assume that you have a cube. And so if I pick 3, let's say I pick in general, I pick n-1 points, and I pick them linearly independently, but all on the same plane. Okay. You can't necessarily, but pretend I'm picking them on the same plane. There's some plane here that contains all of these points. So now the question is, if I pick one more point randomly, let's say I pick anywhere in here. So what is the probability that this point lies on this plane? Well, this is actually pretty easy. And it's like, so if we think about it like a line, right? If we think an analogy would be, if I have a line, I'm asking what's the probability that I pick a random point and it's a specific point that I want. The probability there would be 0, and it's the same thing. So the probability that a random point picked from this cube will lie on the same plane as these other n-1 points is 0. Mm-hmm. As long as n is greater than 2. So if n is greater than 2, then the probability is 0. Probability, and we'll call this statement x. So x is the statement that this randomly picked point lies on this plane. And we'll say x is the statement that is true. This probability is equal to 0. n-1 is greater than 2. So if I have more than 2 points on this plane, and I pick another point, that probability, so the probability that this point lies on this plane is 0. Now, what happens if instead of that, I have n-1 equals 2? Well, then any third point, for any random point I pick, there is a plane that contains all 3 points. So the probability that I can pick a random point and have a plane that goes through there is 1. And it's actually stronger than just probability. It always happens, right? Mm-hmm. So what this is saying is that if I pick 3 random points in a cube, they will always lie on the same plane. And a much stronger statement is this is going to be the only surface where that is true. Now, why is that important? Well, it's important for computers. Computers are really good at handling individual planes, and they're really bad at handling curves, right? And so what we do with computer graphics is we take some big, complicated 3D model and we triangulate it. And then we feed it to the computer in the relative planes that it uses. So this very simple triangle is the backbone for all of the big 3D computer graphics that we're able to see.
Let's see what that looks like. So you're telling me that triangles, what should I search for?
Triangulation of, I don't know, what's something that you like?
Buzz Lightyear.
Sure. Yeah, let's look for that. Well, Buzz Lightyear is already triangulated.
True.
Let's look for let's start with, say, triangulation of a ball.
Okay.
So you can see that what happens is when we see a ball, what we see, or what the computer is actually feeding, is a whole bunch of tiny triangles, each one on a plane, possibly with a different color palette.
I can see these triangles here.
Yeah.
So you're saying I cut out a bunch of triangles from paper and I glued them together.
Mm-hmm.
I could make something that looks like a sphere.
Yeah, you can. And now the thing is that you may have to have, you can make something that looks like a sphere, something much more complicated. And you may have to have the triangles be different sizes to make your complicated thing look right. But yeah, absolutely you can. You can triangulate it. If you go back, so do you see the triangulation where it says topology? So this is the other thing. So as a data scientist, it's very common for us to have huge amounts of data, right? And it's very hard to figure out much about the structure. So one thing we can do is we can take these big manifolds, and you can try and find a manifold that fits, that maybe fits like a cloud of points. But the question is then what do you do with it? How do you analyze it? How do you figure out when two manifolds are the same or when they're not the same? And what you use is this. You do something called triangulation of the manifold. And so from the triangulation, you get this thing called persistence topology out, which you calculate by using the triangulation. So this triangulation allows us to translate these big geometric database things into simple algebra.
That's really, really, really cool. I had no idea that K3 was so deep.
Yeah. And the reason, and there are other shapes that you could use this to do, or that you could do this with, but computers re-triangle so quickly that this is a very efficient way to do it. So you get this persistence topology, and there's a lot of different things. The thing that's used the most, hold on, perfect, yeah. So what you do here is this is your raw data. It's a bunch of points in two space, right? Now, this is very simple raw data, but it could be data, say you're in Facebook, so this could be in 35,000 dimensions or something.
Mm-hmm.
In this one, it's in 2 dimensions, and they're the black points. So what you do is you slowly increase the radius of these points, and you start to see at what point do these balls intersect. And when they intersect, you draw a line between them.
Okay.
And then you keep increasing them. And when you get 3 balls that intersect, you draw a triangle and you fill it in.
So that's a graph though.
Correct.
The
Yes.
radius, that's the circles are vertices and you're drawing the edges between them.
Right. Yeah.
And then you're just also filling in wherever you see a triangle based on, so it goes vertices to edges to triangles.
Right. Yeah.
And triangles to some more complex shape like a sphere.
Right.
Or a dolphin or whatever.
Yeah, and what you want to see are these big holes.
So it gives a shape to information.
Correct. Yeah, absolutely.
Information and
yeah.
it gives you a shape. This is beautiful.
100%. You take this hard, so you have this real hard, complicated, high dimensional data. You describe its shape, but then the beauty is you're able to translate it into something like this